Okay, so let's start. In the last class, we were looking at the sort of geometric interpretation of duality. Right? Recall that our goal is to solve a constraint minimization problem where we have an objective function f0 of x, and we want to minimize this subject to a bunch of inequality and equality constraints. This is our general form of the optimization problem that we're trying to solve. Okay. And the duality approach, the Lagrange dual approach, is to first formulate this dual optimization problem. So given this original problem, you compute a new function which is a Lagrangian, which is essentially a linear combination of the objective function and each of these constraint functions, where each of the constraint functions is weighted by some coefficient which we call the dual or the Lagrange multipliers or the dual variables. Right? When you minimize the Lagrangian with respect to x over the entire domain, not with respect to the constraints, you get the Lagrange dual function, and the dual optimization problem is to maximize the Lagrange dual function over all possible lambda greater than or equal to 0 and over all nu in R to the p. And we saw a few examples where this can be helpful. The constraint optimization problem is much harder to solve than the dual optimization problem. And we'll see many more such examples. But in the previous class, we looked at a geometric interpretation of duality in terms of these epigraph sets. Right? Recall that I first defined this set A as this huge vector, the set of all vectors of the form f1 of x, f2 of x up to fm of x, h1 of x up to hp of x, and f0 of x. So for every single x, you get one such vector, and you list all possible such vectors, and that gives you this particular set A. But the epigraph form of this is what I called G. Right? So it's a set of all vectors u, v, t, such that fi of x is less than or equal to ui, hj of x is equal to vj, and f0 of x is less than or equal to t. So for a given optimization problem, you can, at least if you have, let's say, a single objective, you have one objective function and you have one inequality constraint. In that special case, this G is a subset of R2, and we saw a couple of examples of what it looked like. In this case, the constraint minimum has a nice interpretation. If you look at the left half of this particular plane, then the lowest point that is achieved, the lowest point in G, that corresponds to the constraint minimum. Right? In this case, this point over here, that would correspond to the constraint minimum. Right. When we looked at the dual, that also had a nice geometric interpretation in terms of tangents or supporting hyperplanes to this given set G. Right. So you look at all possible supporting hyperplanes to the set G. Each supporting hyperplane corresponds to one G of lambda comma nu. And the maximizer, that is in this case G of lambda, that essentially corresponded to the intercept along the t-axis. So the dual optimization problem, the solution to the dual optimization problem, that corresponds to the highest t-intercept that you can have among all possible supporting hyperplanes. Right? And you can see, at least visually, that the highest t-intercept for any supporting hyperplane is always going to be below this f star. It can never be above f star. Right? And in certain cases, particularly when this G is not a convex set, you can see that it is possible for there to be a gap between D star and F star. And that is when you have a duality gap. Right? But on the other hand, in general, if G is convex, then the duality gap will be equal to 0. Now, one thing to keep in mind is that I'm not making any statements about KKT conditions over here. It is just to do with duality. It is just whether the minimum of the constrained optimization problem can be equal to the maximum of the dual optimization problem or not. All right. Any questions? Yeah.
Why exactly did we have to shift from like the set A to the like space G? Like we can still create, like we can still find the supporting place with respect to like the set A.
So in general, so just the set A would not be sufficient. You'll have to add some more restrictions. So for example, when I said that when I took this to be the set A, right, you can also have a supporting hyperplane of above, right, in which case the intercept with the t-axis can potentially be above f star also, which doesn't really make sense. Okay, you can try to derive that. You can see what will happen if you try to look at the supporting hyperplanes of A instead, and that does not really give you the dual optimization problem. Okay, and one thing to note is that each supporting hyperplane is essentially defined by this vector, right? Lambda nu 1, correct? One thing to keep in mind is that the last coordinate of this vector, essentially the normal to the supporting hyperplane, this is always equal to 1. This has a special name. It's a non-vertical supporting hyperplane, right? Which means that it can never be parallel to the t-axis, right? Because if this were equal to 0, then effectively that you can think about it for a little while. That will correspond to a supporting hyperplane that is parallel to the t-axis, which cannot happen because for g of lambda comma nu to make sense, the intercept with the t-axis would have to be finite. Okay. So you can interpret g of lambda comma nu as the intercept of some supporting hyperplanes to the set A, but not all supporting hyperplanes. You will see that there's an additional restriction to be imposed on that, and it makes most sense to look at G instead of A. Some portion of A will lie on, if it has a minimum, yeah. So if it is feasible and there exists a finite minimum to your original optimization problem, then definitely yes. In fact, it will at least intersect on the t-axis, right? In this case, the lowest intercept of A on the t-axis, that will correspond to the constraint minimum. Yeah, right. Again, all of this is in 2 dimensions only. It's a very restricted class of optimization problems, but you can generalize this, of course, to higher dimensional spaces. This nice geometric interpretation is visual in the case of 2 dimensions, but for higher dimensions, it's slightly more complicated. Okay. Any other questions? Just a word about notation. I kind of switched, so I called this set over here to be equal to A, and the epigraph form to be equal to G, but the book by Boyd and Vandenberg essentially switches this, so that's something to just be careful about. It calls this set G and this set A, but the meaning is still the same. All right. Okay. And towards the end, we also saw that a sufficient condition for strong duality to hold, for f star to be equal to d star, is this so-called Slater's condition. Now, this is what is called a constraint qualification. So essentially sufficient conditions on your constraints so as to satisfy strong duality. Okay, Slater's condition is one such condition, which is the most popular condition that is known. But you can have many other constraint qualifications for different optimization problems. Okay, and you may all, and this, of course, while we've stated it for convex optimization problems, there are also very specific subclasses of non-convex optimization problems where if Slater's condition holds, then strong duality also holds. But these are very specialized and we will not really explore them in any detail. Right? Okay. So we'll explore duality in some more details and we'll also complete the picture with respect to the KKT conditions. There was one small part in the KKT conditions that we didn't really prove, which was essentially that for every I, lambda I times fi of x should be equal to 0. That somehow didn't seem natural. It came out of nowhere, and we'll see why that is the case, why that has to hold. And in fact, we'll prove, in some sense, we'll prove all the KKT conditions in this particular class. All right. But before that, okay, so let me first do that perhaps. So recall that, let's again recap the optimization problem. Minimize f0 of x subject to fi of x less than or equal to 0 and hj of x equal to 0 for j between 1 and p. Right? The Lagrangian L of x lambda nu is equal to f0 of x plus sum over I lambda I fi of x plus sum over j nu j hj of x. And g of lambda comma nu is equal to the infimum of L of x lambda nu over all possible x in the domain. Okay. Now recall that if strong duality holds, yeah.
In this condition, we know that the problem is convex.
Correct. Yes.
Then, if problem is convex, then the relative interior conditions satisfied. Then we say that this is a strong duality.
So that's a sufficient condition for strong duality. If the problem is convex and there exists some x in the relative interior, for which all of these inequalities are satisfied with strict inequality, then we say that this satisfies strong duality.
If strong duality holds, KKT conditions are necessary.
If strong duality holds, then KKT conditions are necessary. Yes.
But when we are saying that strong duality holds, we are implicitly imposing the condition that problem is convex.
No.
If problem is, that is what the Slater's condition is.
No, that's so Slater's condition is valid. So if Slater's condition is satisfied, then and the problem is convex, then this satisfies strong duality, right? But Slater's condition is not necessary. There are plenty of problems which satisfy strong duality and do not satisfy Slater's condition, right? But for all of them, KKT conditions are necessary. Yes. So basically, if Slater's condition is satisfied for a convex optimization problem, then the KKT conditions become both necessary and sufficient.
If the problem is
So this is Slater's condition, but just because Slater's condition is satisfied does not necessarily mean that strong duality is satisfied. For certain subclasses of non-convex optimization problems, slight generalizations of convex, So it should be approximately convex in some sense. That is only one way. It is one set of what are called constraint qualifications. Okay. So now coming back to what I wanted to show. So suppose that I have a minimization problem, a constraint minimization problem, and suppose that it satisfies strong duality. All right. So if strong duality holds, then basically f star should be equal to g star. Right? So f star, and I'm assuming that this f star is achieved by some point. Let me call that x star. Okay. So this is equal to f naught of x star, where this is the constraint minimizer. So x star satisfies all of the constraints and it achieves the minimum among that entire constraint set. So if this holds, then of course this should be equal to d star, right? But what is d star? It is g of some lambda star nu star, where x star is equal to x star satisfies the constraints, lambda star is greater than or equal to 0. Right? So lambda star nu star correspond to the maximizer of G, and x star correspond to the minimizer, the constraint minimizer of F. All right. But what is G of lambda star? So let's fix G of lambda star nu star. So let's fix nu star and lambda star. That is true, yes. So it's R max subject to this constraint that lambda should be greater than or equal to 0. All right, but let's look at the definition of G. This is equal to the infimum over all x in D of L of lambda star nu star, of L of x lambda star nu star. So let me just write that out in full. F naught of x plus summation I equal to 1 to m lambda I star fi of x plus sum over j nu star hj of x. Right, so this is equal to this, right? But this is less than or equal to, now this infimum is taken over all possible x in the domain, right? So obviously if I minimize over a smaller set, then that quantity can only be larger than this. So this is less than or equal to the infimum over all x in the constraint set of this particular object. Okay, but what is the x that achieves the minimum on the right hand side? Yeah, x star so let me put it in a slightly different way. So this is the minimum over all possible x. All right, let me say the following. this is certainly less than or equal to any particular x, right? If I plug in a particular x on the right hand side, then obviously the value of this particular function will be greater than or equal to the minimum value, right? And let me choose that x to be x star, right? What you should keep in mind is that the minimizer of this function may not be the minimizer of f0, right? That's one thing to just keep in mind, because um, for every x in the constraint set, so firstly, this minimization is not performed over the constraint set, it's performed over the entire domain. So potentially this could be even smaller. But even over the constraint set, this quantity is equal to 0, right? Because for every x in the constraint set, hj of x should be equal to 0. But you also have these terms fi of x, which you know are less than or equal to 0. That's it. So potentially you could choose an x for which fi of x is really small, and that kind of dominates this function compared to f0. But nevertheless, this is less than or equal to f0 of x plus this particular quantity. Okay, but what is the last term equal to? It's equal to 0 because x star should satisfy the constraints. So hj of x should be equal to 0. So the last term is anyway, this quantity is 0. What about these quantities? What can you say about these? Yeah, they are less than or equal to 0, right? Because each fi of x is less than or equal to 0, and lambda I star should be greater than or equal to 0. So each of these is less than or equal to 0. So this overall quantity is less than or equal to f0 of x star, right? The only assumption that we have made so far is that strong duality holds, nothing else, right? So if strong duality holds, then this is less than or equal to the right hand side. But can you have strict inequality? What do you have on the left hand side? Left hand side is f0 of x star, the right hand side is also equal to f0 of x star, which means that each of these should be an equality, not just an inequality, right? So as long as strong duality holds, so if strong duality holds, then you must have this being an equality and this being an equality. All right. So let's focus on the second inequality first. So this will be an equality only if each of these terms is equal to 0. Right? So which must mean that lambda I star fi of x star, this should be equal to 0 for all I. Okay, remember this is a necessary condition. If strong duality holds, then this must be satisfied. And these are what are called complementary slackness conditions. Earlier you had lambda I star fi of x star should be only less than or equal to 0. But what this demands is that should also be in some sense greater than or equal to 0. So this is equal to 0. Right? Remember that this is a necessary condition. Now let's focus on the other inequality. What does that inequality say? It says that if I take the minimum of this, the Lagrangian, evaluated at lambda star nu star, and I minimize this with respect to all possible x over the entire domain, then this will be exactly equal to f0 of x star. Right? So this is one property that we have derived. If strong duality holds, then the complementary slackness conditions must be satisfied. The second condition that we have is that if strong duality holds, then f0 of x star is exactly equal to the infimum over all x in D of f0 of x plus summation over I lambda I fi of x plus summation over j nu j hj of x. Okay, remember the main point to focus on here is that this minimum is taken over all possible x. Now if all of these fi's and hj's are differentiable, then how do you find the minimum? Differentiate and set it equal to 0. So the stationary point should be equal to the point of minimum, which means that if I take the gradient with respect to x of the Lagrangian, set it equal to 0, then the only point that satisfies this is x star, or certainly x star must necessarily satisfy this particular point. Gradient f0 of x star plus summation over I lambda I fi lambda I star fi of x star plus summation over all j nu j star hj of x star. This should be equal to the 0 vector. Again, this is a necessary condition, right? If this function is not convex, right, if these functions are not convex, then potentially you can have other stationary points other than the points of minimum. But this becomes sufficient if x star is actually, if all of these fi's are convex. If fi's are convex, f0 is convex and hj is affine, then this also becomes a necessary condition. This also becomes a sufficient condition. So that was the second point that we got just by assuming strong duality. Now, of course, since x star as well as lambda I star nu star should satisfy all of the constraints, the corresponding constraints, we must have lambda I star should be greater than or equal to 0 for all I, and fi of x star should be less than or equal to 0 for all I, and the last point being that hj of x star should be equal to 0 for all j. So this is the complete set of the KKT conditions. Why can't you fix lambda to be 0? Because you can have problems wherein lambda I is non-zero. Which one? Okay, so lambda I times fi of x star is equal to 0, right?
Like, wherever we use it, anywhere we just get 0 on there. Why don't we just eliminate from
Because in many cases it may so happen that, so I don't have a good example right off the bat, but there are conditions wherein you will need lambda I to be non-zero, but fi of x star should be equal to 0. Okay, and you can see that one of the reasons where this kind of comes up is this condition should be satisfied. Right here, all of this is with respect to the gradients. So there could be a even though maybe fi of x star is non-zero, or fi of x star is equal to 0, the gradient may not be equal to 0. So maybe by the next class I'll come up with an example where you need both lambda I to be equal to 0 and not equal to 0. In fact, I think probably in some of the examples that we've seen previously, we did require the lambda i's to be non-zero. If you go back to the water filling problem, I believe the lambda I did have a non-zero value. Okay. Any other questions? Okay, so that gives us the KKT conditions. Right, which gives us a way of analytically trying to find the minimum. Right? We saw a couple of examples where we tried to get closed form expressions for the minimum, kind of the water filling solution, as well as minimizing the entropy and so on. Right? But in practice, you don't really try to get closed form expressions for the solution. For most problems, you cannot do that. What you instead will try to do is try to design an iterative algorithm that will eventually converge to the solution. Right? For one such example was gradient descent, right? Something like gradient descent. But you saw that even in gradient descent, there is the problem of finding out what the right step size is. That was number one. Number two, how do you decide, or how do you know whether you've reached the solution or not? Correct? So in most problems, you will never converge exactly to the solution. At best, you get close to the solution. Right? So in such scenarios, how do you decide? One way to typically decide is that eventually if 2 points are close to each other, right? If your current iterate and the next iterate are within a certain epsilon, then you stop. Okay? Which in many cases is okay for a convex optimization problem. But suppose I give you a non-convex optimization problem and this happens, right? How do you know whether you're stuck at a local minimum or you're actually close to the global minimum? In general, you can't. Right? But this idea of duality lets you come up with iterative algorithms where you can say, even though you don't know what the minimum value is, you know whether you're close to the minimum or not. All right? So let's see why that is the case. So remember that if you have strong duality, then g of lambda or g of lambda star nu star will be equal to f star. Okay. Now there are a class of iterative algorithms where in each step you don't just choose x. So you essentially try to jointly solve both the primal optimization problem as well as the dual optimization problems. So let's suppose that I have an algorithm So we have an algorithm that produces for each iteration Let's call them xk, lambda k, and nu k. So in each iteration, you find some xk, you find a lambda k, you find a nu k. Doesn't matter how you get these. Okay. Now, you know that g of lambda k and nu k is always going to be less than or equal to f star. That is guaranteed. Correct? And yeah, so g of lambda k nu k for each iteration, this is for sure, you know, this is going to be less than or equal to f star. Okay. Let me just add f0 of x star on both sides. Sorry, f0 of xk on both sides. So f0 of xk plus g of lambda k nu k is going to be less than or equal to f0 of xk plus f star. Okay, so this holds for any iterative algorithm in general that produces some set of points xk, lambda k, nu k, which satisfy the constraints. So xk should satisfy all of the primal constraints, and lambda k should satisfy the dual constraints. That's something that we require. But otherwise, we don't care how the algorithm works. It may be gradient descent, it could use something else. Now let me bring f star to the left hand side and move g to the right hand side. What do I have? I have f0 of xk minus f star is less than or equal to f0 of xk minus g of lambda k nu k. Right, which is great because what is the left hand side? Yeah, correct. So it's how far you are away from the optimum, right? So this is the gap to optimality. So your optimality gap is always upper bounded by this so-called duality gap. Right? So if the right hand side, you know xk, you know lambda k, you know nu k. If the difference between these two functions is less than or equal to epsilon, then you know for sure that f0 of xk is at most f star plus epsilon. Right? So now how do you define a stopping rule? You keep running these iterations until this duality gap is less than or equal to epsilon, and then stop. Okay, so even if the subsequent xk's are not close to each other, they could potentially be a little far away. Even if that happens, this is one way of checking whether you're close to the optimum or not. So one stopping rule is that f0 of xk minus g of lambda k nu k, this is less than or equal to some target epsilon, and you can stop here. In the next few classes, we'll see a few basic iterative algorithms that let you solve general convex optimization problems. But maybe in this class, I'll talk about slight generalizations of what we've already seen. We assume that the optimization problem that was given to us satisfied could be framed in terms of the general optimization framework. But you can generalize this even further. Right? The KKT conditions and so on, this whole theory of duality can be extended to not just satisfy these inequalities, but you can also have generalized inequalities. So let's look at a slightly general formulation of the optimization problem. So let us look at the following slight generalization, which is as follows. So you want to minimize some f0 of x subject to some hj of x equal to 0, 1 less than or equal to j less than or equal to p. So you still have p equality constraints. But in general, your inequality constraints fj of x may not be real valued inequality constraints. So in the sense that each fj need not be a function from rd or rn to r. It could be a function from rn to some rk. And I could have some generalized inequality ki less than or equal to 0. Okay. Now, what is the consequence of having such a slightly more general framework? Pretty much everything remains the same. The dual optimization problem is framed exactly in the same way. So in this case, the Lagrangian one thing to note here is that each fj is not a function from Rn to R, it's instead a function from Rn to some Rki, for example, or Rkj. So the Lagrangian will have j variables, one for each equality constraint, and it will have not m variables. I mean, in some sense it will have m, but each of those will have to be a vector. Okay, so the Lagrangian will be a function of x, and you also have lambda 1, lambda 2 up to lambda m, where each of these lambda i's is a vector, and nu, which is going to be equal to summation is equal to f0 of x summation over I, the inner product between lambda I fi of x summation over j nu j hj of x. Hj is a function from Rn to R. I mean, because anyway these are equality constraints. So even if they're vector valued, it's effectively the same. the Lagrange dual function is defined exactly as before. Is equal to the infimum over all possible x in D of the Lagrangian. But it is in the formulation of the dual optimization problem where you have to be a slightly careful. The dual optimization problem would be you maximize g of lambda 1 up to lambda m nu subject to the following constraints, that each lambda I, remember that each lambda I is a vector, so it's greater than or equal to 0, but this is going to be a generalized inequality, and this generalized inequality will be with respect to the dual cone. I'm sorry. So k star is the dual cone of k. Each ki star is the dual cone of ki. This is ki star. So this is ki star. Whereas in your primal optimization problem, again, you have to remember that this inequality goes the other way around, and this is with respect to the primal cone, ki. Okay, so let's see a couple of examples of such problems. So we'll maybe see some general examples instead of specific ones, general classes of optimization problems. The first is what is called a semi-definite program, okay, wherein you want to ensure that certain, so typically in such semi-definite programs, you would want to solve some kind of a minimization problem subject to where the variables are actually in the form of matrices, and you want to ensure that these matrices are positive semi-definite. So one very common example where a semi-definite program arises is when you want to do some kind of power allocation. You want to find, let's say, maximize some kind of a rate term, and you're allowed to allot different powers to different channels, similar to what we saw in the water filling problem. But now in these channels, you can allocate power not independently. Instead of transmitting independent data across each of these sub channels, you are potentially allowed to transmit correlated data, and that is something that arises in multi-antenna communication, for example. So semi-definite program. Right? So the general form of a semi-definite program, again, there are many different versions, but the simplest version is the following. You want to minimize a linear function some C transpose X subject to, of course, you can have some equality constraints, but let's not worry about that. Maybe I want some G plus summation I equal to 1 to n xi fi is PSD. And this positive semi-definiteness arises out of physical constraints. So in random processes, have you encountered positive semi-definite matrices anywhere? Covariance matrices, right? So covariance matrices are always positive semi-definite, and this is one class of examples where you will have such constraints, right? So suppose you want to find some kind of a distribution. Let's say you want to maximize the entropy subject to the constraint or subject to all possible overall possible Gaussian distributions for which the covariance matrix is it satisfies certain constraints, right? Which arises which can be posed as this positive semi-definiteness constraint. Right? So this would be the general SDP. I can write this as you minimize C transpose X subject to G plus summation over I xi fi should be, let's say, greater than or equal to well, let me pose it in a slightly different way. Okay, fine, doesn't matter. This is greater than or equal to 0, right? And what is the k in this particular case? What is the cone? The cone of all positive semi-definite matrices. It's basically S n plus. All right. What would the dual be in this case? Let's formulate the Lagrangian L of x, comma. Now I have to be able to formulate sort of a dual program. So the Lagrange variables will in fact be a matrix. The Lagrange multipliers. So I'll collect all of the Lagrange multipliers in terms of an n by n matrix. I'll call it Z. This is going to be n by n symmetric. So I don't really have n square many entries. I only have n into n plus 1 by 2 entries, or n into n plus 1 by 2 distinct entries. This will be equal to, what will this be equal to? It will be equal to f0 of x plus an inner product between z and this particular quantity. These are all matrices, keep that in mind. So how many, so what would be the inner product? What would be a natural choice of inner product between matrices? Trace of the product, right? Trace of the Frobenius. So that will be equal to plus the trace of z, instead of, I don't need to take z transpose because everything here is symmetric. My assumption is that each fi is a symmetric matrix. Fi may not be positive semi-definite. Why is z is symmetric? That's how I'm going to choose my, because everything is going to be defined with respect to a certain cone, right? Because even if you think about this, my assumption of course is that each fi is symmetric, correct? So how many constraints do I have? Correct. So if I didn't have the constraint that fi's are symmetric, then I would have n square many constraints, because this gives me a matrix, an n by n matrix, and I want each entry of that matrix, whatever, I have some constraint in terms of positive semi-definiteness over here. But loosely speaking, you can think of it as n square many constraints, right? But here, since each fi is symmetric and g is also symmetric, effectively I just have n into n plus 1 by 2 many constraints. Okay. All of these are symmetric. But may not be positive semi-definite. So I need roughly those many Lagrange multipliers. I'll have n into n plus 1 by 2 Lagrange multipliers. This is a trace of z times g plus summation over I xi fi but I can sort of expand this out. What is, let me write this as f0 of x plus trace of z times g plus summation over I xi g fi. Yeah. I'm sorry, did I miss something? Sorry. ZF. Thanks. Okay, but what is the trace of sum of matrices? Yeah, the sum of the traces. So I can write this as equal to f0 of x plus trace of z times g plus summation I equal to 1 to n xi times trace of zfi. But what is f0 of x equal to? It is C transpose x, which is just summation Ci fi. Sorry, Ci xi. Let me write that down. I equal to 1 to n Ci xi, which is equal to the trace of z times g plus all, I'll take all of the terms that multiply with xi together. Summation I equal to 1 to n xi times ci plus trace of zfi. So this is my Lagrangian. What is g of z going to be equal to? It is the infimum over all possible x in Rn of L of x comma z. What will that be equal to? So what kind of a function is this of x? Affine, right? So there's some constant plus a linear, it's an inner product of x with some vector. So now what would the minimum over all possible x of this quantity be equal to? Yeah? Trace of y? Yes, but there are no constraints on x. Yeah? Minus infinity always? Unless? Yeah, unless this quantity is equal to 0 for every single I. So this will be equal to minus infinity. Okay, let me the other way around. So if each one of these terms is equal to 0, then this is just a constant function. It is just trace of z times g. This trace of z times g if ci plus trace of z times fi is equal to 0 for all I. Yeah. Sorry, I think my bad. I made a little mistake over here. Remember that this was a greater than or equal to constraint. I should have converted that to a less than or equal to constraint first. So in fact, all of these should have been negative signs, because I would have minus g minus summation over this should be less than or equal to 0. Plus so in other words, each trace of z times fi should be equal to ci for all I. And it's equal to minus infinity otherwise. I think there should be a negative here also. Right? So what would be the dual optimization problem? Maximize so you maximize the negative of the trace of z times g subject to Okay, so Z should be greater than or equal to, with respect to K star, 0, and the trace of Z times Fi is equal to Ci for I equal to 1, 2, 3 up to n. But so it's K star, right? With respect to K, correct. Yeah, but that's the same as saying that the negative of this is less than or equal to 0. No. The inequality still remains the same, right? So the negative, so this greater than or equal to 0 with respect to K is the same as the negative of this less than or equal to 0 with respect to K. Because it's as though you're subtracting the same quantity from both sides, right? Remember the properties of the generalized inequalities. If x is less than or equal to y, then x plus z is less than or equal to y plus z.
Less than or equal to 0 with respect to minus.
Is sure, but that's the same as this quantity being less than or. Okay. All right. So, but what is K star in this case? The dual of the PSD matrices, set of all PSD matrices, but in this case there is also PSD. So this is the same as saying that Z is PSD. So the dual of a semi-definite program turns out to be another semi-definite program. Right? So you have a bunch of linear constraints on Z, and that Z should be PSD. And what kind of a function is this? This is also linear in Z. Which one? It's not a linear program because the constraints are not all linear. So that's why this is called a semi-definite program. It's one step above being a linear program because this is the only other constraint, on a non-linear constraint that is applied. Another very similar or slightly generalized version is a conic program, wherein you again want to optimize a linear function subject to conic constraints. Question? So again, you want to minimize a linear function some C transpose X subject to a constraint that we can have some linear constraints Ax equal to B, and that X should be less than or equal to 0. Okay. Where this K can be any proper cone. Okay, it need not be the positive semi-definite cone, it could be anything. For example, it could be even, let's say, a vector space. It could be a vector space. It could be the ice cream cone. It could be any norm cone. It could be a positive semi-definite cone. Anything. So once again, let's try to compute the Lagrangian. This is the function C transpose X plus lambda transpose X plus nu transpose into AX minus B. Or this is minus nu transpose B plus C plus lambda plus A transpose nu transpose X. It's called a conic program again because we have these different classes because you can come up with numerical optimization problems that work well for each of these specific classes of programs.
Previously, the constraint is on the matrix.
A semi-definite program because it's a semi-definite optimization. So here K is a cone, right? It's a proper cone. That's why it's called a conic program. So in fact, until fairly recently, a couple of decades ago, people used to study each of these optimization problems separately, right? So first people studied linear optimization problems. You had a bunch of very good solvers that could solve any linear program efficiently. Then people started trying to expand this, try to solve more general optimization problems. They defined these semi-definite programs, conic programs. Of course, each of these arose naturally in certain problems, different sub areas, but people used to try to solve each of these separately. So there are specialized solvers for each of these programs. But then people later found out that you can in fact put all of these under the broad umbrella of convex optimization and try to come up with a general solver. Of course, it can solve it efficiently, but then if you have a specialized solver for conic programs, you could potentially use that because that will be more efficient than one that is tailored for a general convex optimization problem. In fact, when you use CVXPy, right, CVXPy is not a solver in itself. Okay, it's only something that lets you input a convex optimization. It will first check whether the optimization problem is convex or not by checking for certain constraints. And once it's satisfied that it is a convex optimization problem, it tries to identify what kind of an optimization problem is it. Is it a conic program? Is it a semi-definite program? And then it picks one of these solvers. There are a bunch of different solvers. It will pick the most appropriate solver and try to solve that numerically using them. In fact, when you try to use CVXPy, if you go through the manual, you'll see that you can also specify which solver you want it to use. There are a bunch of default solvers, but you can add more packages and force it to use specific solvers if you're really interested in getting the best performance. Okay, so it's helpful to know what kind of a problem you're facing. Just by knowing that your problem is a conic program, you can use a conic solver. Okay, so once again, what is the Lagrange dual going to be equal to? It's the infimum of this with respect to all possible x. What will that be? It will be minus nu transpose B if C plus lambda plus A transpose nu is equal to 0, and it's equal to minus infinity otherwise. Right? So what is a dual program? You want to maximize minus mu transpose B subject to, first lambda should be greater than or equal to 0 with respect to k star, and you want C plus lambda plus A transpose nu to be equal to 0. You can simplify this a little bit, the same as saying maximize minus nu transpose B. I can rearrange this to have lambda is equal to A transpose nu plus C, or minus A transpose nu minus C, right? And lambda should be greater than or equal to 0. So the same as saying minus A transpose nu minus C is greater than or equal to 0. Now, there's also another reason why these sort of classes are different. Note that suppose you want to solve a semi-definite program, you find the dual, you see that it ends up being another semi-definite program. You take a conic program, you want to solve it numerically, you find the dual, that also ends up being another conic program, because you have the constraint that minus A transpose nu minus C is greater than or equal to 0 with respect to, now it's now with respect to a different cone, with respect to the dual cone, right? So at the face of it, if you want to solve any general conic program, just going to the dual doesn't really help. Okay. So you need some other method in order to be able to solve this conic program. This is the dual conic program is no easier in some sense than the original primal conic program. You need to be able to solve some conic program. Maybe by going to the dual, the number of dimensions reduces. That's one possibility. Maybe it becomes easier in computationally, but in principle, it doesn't reduce the difficulty in solving the original program. Okay. So in the next few classes, we'll see some more examples, some more specific examples of optimization problems and how to solve them using Lagrange multipliers, KKT conditions. And then we'll also see a few algorithms that can be used to numerically optimize. So far we've seen a few examples where we used CVXPy as a black box. You just input something, you get it out. But how does it really work? What kind of algorithms actually go into solving these programs? Okay, so let's stop here.